Have you ever encountered a software bug that seems to vanish the moment you try to investigate it? It works fine one moment, then inexplicably fails, only to work again without any changes. These elusive issues can be incredibly frustrating for any developer or user. Non-deterministic software faults, often referred to as Heisenbugs, are caused by a complex interplay of external factors or specific execution environments that are not consistently replicated. This leads to unpredictable behavior, meaning the same code might run perfectly fine many times, but occasionally fail without a clear, repeatable trigger. They are not errors in the static code logic itself, but rather emerge from dynamic interactions. The core mechanism behind these faults is usually a dependency on elements outside of the program's strict, controlled execution path. A common culprit is concurrency, such as race conditions where multiple threads access shared resources without proper synchronization, or deadlocks where threads mutually block each other. These issues depend on precise timing, which is rarely identical across runs. Other significant factors include interactions with external systems like network latency, database response times, or file system access speeds, where delays can alter program flow. Environmental variables such as operating system scheduling, memory allocation patterns, processor cache states, or even intermittent hardware glitches can also contribute. Ultimately, any timing dependency or reliance on uninitialized memory that takes on arbitrary values can lead to this unpredictable behavior. To tackle these unpredictable issues, developers often employ a range of diagnostic strategies. Detailed, timestamp logging can help capture the system's state just before a failure, offering crucial clues about the environmental conditions at that moment. Aggressive system monitoring is also vital, allowing observation of resource usage, network traffic, and process states during runtime. Replicating these faults often requires creating highly controlled test environments to isolate variables, and sometimes involves stress testing the software under heavy loads or unusual timing scenarios to expose hidden dependencies. Implementing robust defensive programming techniques, such as careful synchronization primitives and thorough variable initialization, can also significantly reduce their occurrence. The term Heisenbug itself is an insider detail, inspired by Werner Heisenberg's uncertainty principle in quantum mechanics, which posits that the act of observing a system can change it. Similarly, when you add debugging tools, logging, or even just slow down execution to observe a Heisenbug, the very act of observation can alter the timing or environment enough to make the fault disappear. It highlights the unique challenge these bugs pose, not just as logical errors, but as problems of managing chaotic and dynamic system dependencies. Ultimately, understanding the varied and often subtle causes of non-deterministic faults empowers developers to shift their debugging strategies. Instead of solely focusing on linear code inspection for logical errors, they learn to expand their approach to comprehensive system observation and environmental analysis. This broader perspective is essential for developing more robust and reliable software systems that can gracefully handle the complexities of real-world operating conditions.
If this helps you fix faster, like, subscribe, and keep debugging with us.